All right. Moving on to 10.2. In 10.1, we briefly kind of introduced the idea of hypothesis testing and some of the language that we use when we're doing hypothesis testing. That was in 10.1. Sorry, I don't know if I misspoke a second ago, but in 10.1, we talked about all that stuff. Now in 10.2, we're going to talk about hypothesis tests specifically for proportions, when we're testing proportions. In 10.3, we'll talk about tests for means, and in 10.4, we'll talk about tests for standard deviations. But for now, we're going to focus on proportions. So let's consider an example to think about this. Let's say that 83% of people say that they like unicorn giggles, our favorite subject. But you think that that percentage would decrease if they were subjected to an episode of some cartoon unicorn TV show, right? So maybe they're going to get annoyed by the unicorn giggles because of this kids show that they're forced to watch, right? So you guess that the proportion is actually less than 83% after they watch this show. Well, the null hypothesis, as we discussed in the previous section, is a statement of no change, no effect. So the null hypothesis would be that no, people aren't going to be affected by watching this TV show, right? Still, 83% of people are going to say that they like unicorn giggles, right? So P equals 0.83. The alternative is that the percentage decreases, right? So the alternative is that P is less than 0.83. That's what we're trying to show. That's what we suspect to be the case, so it's what we're going to try to show is true. So now the question is, how do we test this hypothesis? Well, we would run an experiment. In this case, let's say that we make 50 people watch an episode of this show, and then we ask them if they like unicorn giggles. Okay, so far so good. Let's say that 76% of your participants say yes. They answer yes to that question. Now, obviously, 76% is less than 83%. But the question is it different enough from 83% to say that you were right? Okay, is 76% different enough from 83% to say that watching this TV show caused them to sort of lose their enthusiasm for unicorn giggles? Well, to answer that question, we would compute a probability, right? What probability would we want to compute to answer that question? Well, we'd want to compute the probability that we would get 76% if, in fact, the true proportion were 83%. In other words, we want to compute the probability that our sample that we would get a sample proportion of 76% or less if, right, given that the true population proportion is 83%, right? That's the probability that we would want to compute. Turns out that we have all of the tools necessary to compute this probability. This is exactly the kind of probability that we were computing back in 8.1. No, 8.2. So this probability is something that we were computing back in 8.2. Okay, so we know how to compute these things. We know that p hat is normally distributed under certain conditions. And so we can use the normal calculator in StatCrunch to compute this probability, right? This probability is called the p-value for this experiment, okay? There are a lot of p's in hypothesis testing, and that's unfortunate. I wish they would use a different letter, but I think they're using p for probability. Anyway, I don't make the rules, but this probability is called the p-value, okay? The p-value of a hypothesis test is the probability that we would collect a random sample that yields the sample statistic that we obtained, or something more extreme, assuming that the null hypothesis is true. And I just realized that's a typo, statistic. Okay, so that's what the p-value is. This is a very, very important concept. It is definitely something you are going to be tested on. I'm definitely going to ask you questions on your Unit 3 test about the p-value and what the p-value means. So you need to understand what the p-value is, okay? It's the probability that we would get our sample statistic if, in fact, the null hypothesis is true, right? So we assume that the null hypothesis is true, and then we compute the probability that we get the sample statistic that we obtained. Okay, so we assume that p equals, going back to our example, we assume that p equals 0.83, and then we compute the probability that p hat is less than 0.76. If this probability is small, okay, if this probability is small, then we have evidence. Let me adjust this a little bit. So, okay, so if this probability is small, then we have evidence that watching the Unicorn TV show made people's enthusiasm for Unicorn Giggles decrease. Why? Well, because again, we're assuming that the null hypothesis is true, and then under that assumption, we compute the probability that we would get 76% of people or less who like Unicorn Giggles. If the odds that that would happen are really small, then that tells us it's pretty unlikely, right? It's pretty unlikely that if the true population proportion is 0.83, that we would get a sample proportion of 0.76. And so it casts doubt on the assumption that we made. It makes us think that, well, so maybe the true population proportion is not 0.83 after all. Okay, so it gives us evidence to reject the null hypothesis in favor of the alternative, right? That people are less enthusiastic about Unicorn Giggles if they're made to watch this TV show. Okay, so we can actually, just for the sake of argument, let's go ahead and compute this probability. So remember, we know that p hat is normally distributed with mean p and standard deviation root pq over n. So let's compute the probability. We're going to go to stat, calculators, normal. For the mean, we're going to put in p, which we're assuming is equal to 0.83. For the standard deviation, we're going to put in sigma sub p hat. So we're going to put in square root of pq over n. That would be 0.83, square root of 0.83 times 0.17 divided by n, our sample size. Our sample size was 50, right? You kind of have to go all the way, almost all the way back up to the top of the page to find it. But we said that we were going to sample 50 people, right? So that would have been our sample size down here. So divide by 50. And let's see about how much that is. We'll round to, let's go 3 decimal places. So we've got square root 0.83 times 0.17 divided by 50. That comes out to 0.053. Okay, and now we want the probability that p hat is less than or equal to 0.76. Okay, let's see what we get. So stat, calculators, normal. For the mean, we're going to put in 0.83. For the standard deviation, we're going to put in 0.053. And we want the probability p hat is less than or equal to 0.76. Okay, so there it is. It's about 0.0933. So it's about 0.0933. Okay. So that's that one, right? So our p-value is 0.0933. And remember, we said if we get a small p-value, then that's evidence to support the alternative hypothesis. In this case, it would be evidence to support the claim that fewer than 83% of people like unicorn giggles. So is this small enough, right? We want our p-value to be small in order to reject the null hypothesis, but is this small enough? Well, in order to figure that out, we need to compare our p-value to alpha, which is our level of significance. And we talked about what alpha was in the previous section. Remember, alpha is the probability of making a type 1 error. It's also linked to confidence intervals, right? So for a 95% confidence interval, alpha is 0.05. That means that if you want to be 95% certain that you're not committing a type 1 error, your p-value needs to be less than 0.05. If you want to be 99% certain, then your p-value needs to be less than 0.01. If you want to be 90% certain, then your p-value needs to be less than 0.10. So is our p-value small enough? Well, it depends on what we would choose for our level of significance alpha. Okay. Most of the time in homework problems, that value is going to be given to you. Okay. So you'll know exactly what to compare this number to. So that's sort of the idea. That's the conceptual idea behind p-values and how p-values work, how we compute them, how we interpret them, and all of that. That's not exactly how we're going to compute p-values in the future. In fact, we're going to let StatCrunch do the heavy lifting for us when we compute p-values in the future. If I have, let me peek forward. Yeah, we're just gonna let we're gonna let StatCrunch do this for us. I have an example here where I was gonna do one by hand, but I think I'm just gonna skip it. I might come back to it. Actually, I'll work out the problem, but I'm gonna work out the problem using StatCrunch. Okay, so we'll just let StatCrunch do these things for us. But here is our process in general for testing hypotheses about a proportion P. So we're going to use a 5-step procedure. Okay, step 1 is going to be to determine the null and alternative hypotheses. Remember from the previous section, there are 3 different kinds of tests we can run: a two-tailed test, a left-tailed test, or a right-tailed test. The second step is going to be to compute the z-score corresponding to our p-hat value. That's called the test statistic. And this is the formula for computing the test statistic. We're not going to do any of these by hand. StatCrunch will compute the test statistic for us. And if we're using StatCrunch to get the test statistic, then really, or rather, if we're using StatCrunch to run the hypothesis test, then really we don't even need the test statistic, to be completely honest with you. But StatCrunch will do this, and then StatCrunch will also do step 3 for us, compute the p-value. The p-value that we want to compute is going to depend on the type of test we're running. So for a two-tailed test, this is the p-value that we want. For a left-tailed test, we want this probability. And for a right-tailed test, we want this probability. Okay. And in each of these cases, z sub 0, right, that's your test statistic that you got from step 2. Again, StatCrunch is going to do this for us. So it's even less complicated than it looks here. Okay. What I want you to be able to do for sure, though, is know how to interpret your p-value. Okay, you're going to use this p-value that you get in step 3 to decide whether or not to reject the null hypothesis. And here's how you make that decision. If your p-value is less than your level of significance, alpha, then you reject the null hypothesis. Again, we talked in 10.1 about rejecting the null hypothesis versus accepting the alternative. They're not the same thing. We never accept the alternative. We either reject the null hypothesis or we don't reject the null hypothesis based on whether the p-value is less than alpha or not. And I'll give you a clear example. I'll try to come back to this idea and so that we can talk in more detail about why we use the language that we do, okay? Once you've made your decision, then you're gonna write a conclusion. And again, talked about that in 10.1. So I wanna give you an example of doing this from beginning to end. Before we are able to actually run this test, we actually have to check that p hat is normally distributed, which means that we would check the same conditions that we're used to having to check, right? I'm not going to make a huge deal out of checking those conditions. In practice, it is something that you would need to do. I'm more interested in just actually running the hypothesis test. So, okay, so let's do it. Real quick, if you skip forward to page 3, then you'll notice that at the top of the page, I have a stat crunch procedure for how to run the hypothesis test using StatCrunch. And basically, you do it the same way that you constructed intervals, that when we were doing confidence intervals. So you're going to go to stat, and then proportion stats, and then one sample, and then you're going to say either with data or with summary. The difference is that instead of clicking on the confidence interval button, you're going to click on the hypothesis test button. And you need to enter the appropriate hypothesis test into StatCrunch. So let's go back to example 1 here at the bottom of page 2. And let's run this example using StatCrunch. Okay, so it says, according to the Centers for Disease Control and Prevention, 19.6% of children aged 6 to 11 years are overweight. A school nurse thinks that the percentage of 6 to 11-year-olds who are overweight is higher in her school district. In a random sample of 65 6 to 11-year-olds in her school district, 13 of them are overweight. At the alpha equals 0.01 level of significance, is there evidence to conclude that the percentage of 6 to 11-year-olds who are overweight is higher in her school district? Okay. Well, let's run the test. Okay, so step 1 is to state the null and alternative hypotheses. Okay. The null hypothesis is a statement of no change, no difference, no effect. So in this case, the null hypothesis would be that the children in this particular nurse's school district are the same percentage of children are overweight in this nurse's school district as they are everywhere else, right? So the null hypothesis is that the proportion is 0.196, just like it is everywhere else. The alternative hypothesis is the statement that we're trying to build up evidence to support. In this case, the nurse suspects that the percentage who are overweight in her school district is higher. She thinks that the percentage is higher, right? So she thinks that P is greater than 0.196. Okay. Well, what sample evidence does she have to make her think that that would be the case? Well, her sample evidence is right here, right? It says in a random sample of 65 of her students, 13 of them were overweight. So in other words, her sample proportion was 13 out of 65, right? That was the sample proportion of students who were overweight in her school district. So let's see, 13 out of 65. is 0.2. So this comes out to 0.2 on the money. So 0.2 is definitely bigger than 0.196. The question is it different enough? Is it a big enough difference for us to conclude that the null hypothesis should be rejected? Well, the only way to figure that out is to compute the p-value corresponding to this sample proportion. So we'll do that in steps 2 and 3. And both of these things are going to be done in StatCrunch. Okay, we're going to go to Stat, Proportion Stats, one sample. And we don't have the data here. We have a summary of the data, so we're going to say with summary. Okay, let's do that and see what we're prompted for. We're going to go Stat, Proportion Stats, one sample, with summary. We're prompted for the number of successes and the number of observations, right? So in this case, the number of successes was 13, right? 13 of her students were overweight. The number of observations was 65, right? That was her sample size. So we'll enter those values, 13 and 65. And then we want to run a hypothesis test, right? We don't want a confidence interval this time. We want a hypothesis test. So we need to state our null and alternative hypotheses. So the null hypothesis was that p equals 0.196. You'll notice that when you change this number automatically changes. And then we wanted this to be a right-tailed test, not a two-tailed test. So I'm going to change this so that it's a right-tailed test. Okay, and then that's it. We're ready to run this test. You don't need to change this level down here. This is only if you're constructing a confidence interval, which we're not trying to do right now. So we're ready. We'll just go ahead and hit compute. And we get a whole bunch of stuff. Okay, here's the number of successes. Here's the number of trials. Here's the sample proportion, which we already computed, right? We already computed that. The things that we're really after are these things. The z-stat, the thing that they label z-stat, that's your test statistic. Okay, so your test statistic is about 0.081. And your p-value. Now this is the thing that's, the p-value is the thing that really is important, because that's what we're going to use to make our decision now in step 4. Our p-value is 0.4676. Okay, so that takes care of steps 2 and 3. Now step 4 is to make a decision. The decision we're trying to make is whether or not we should reject the null hypothesis. The way we make that decision is we compare our p-value to alpha. If the p-value is less than alpha, then we reject the null hypothesis. So, let's see, our p-value, 0.4676. And alpha in this problem, alpha was 0.01. Okay, so 0.01. In order to reject the null hypothesis, we need the p-value to be less than alpha. So we need that statement to be true. And in this case, it is not true, right? This is not true. So our p-value is not less than alpha. So we do not reject the null hypothesis. Okay, we do not reject the null hypothesis. We're not saying that we accept the null hypothesis, right? We're not saying that the null hypothesis is true. We're just saying that we don't have enough evidence to reject it. Okay, and we'll talk about that in a little more detail in a second. Let's go ahead and write down our conclusion now. So in conclusion, we would say this. We would say at the alpha equals 0.01 level of significance. Okay, we are not rejecting the null hypothesis, so that means there's not enough evidence to support the alternative, right? And so there is not sufficient evidence to support the claim that, well, what is the claim, right? So there's not enough evidence to support the claim made by the nurse, right? There's not sufficient evidence to support the alternative hypothesis, right? So there's not enough evidence to say that the proportion of overweight students is higher in this nurse's school district than it is elsewhere, right? So that's what we would say. Another thing you could do is, if you look at the last statement, it says, is there evidence to conclude that the percentage of 6 to 11-year-olds who are overweight is higher in her school district? Well, if you rephrase, that's basically your alternative hypothesis right there. So you could almost copy and paste that phrase. You can say, no, there's not sufficient evidence to support the claim that the percentage of 6 to 11-year-olds who are overweight is higher in her school district, right? So so you could literally just kind of copy and paste it. So there's not sufficient evidence to support the claim that the percentage, I'm just going to kind of abbreviate it a little and say the percentage of overweight students is higher in this nurse's district. Okay, and that's the conclusion. So, and again, we talked about the conclusion in 10.1 and how to write a good conclusion, but just to remind you, your conclusion basically needs to contain 3 things. You need to state your level of significance, then you need to say whether or not there's sufficient evidence, okay, and then you need to restate the alternative hypothesis in words. So in our case, we are not rejecting the null hypothesis. That means there's not sufficient evidence to support the alternative. So, so that's that. So now, just to briefly kind of discuss that, saying that there's not sufficient evidence to support the alternative is not the same thing as saying that the null hypothesis is true. We're not saying here that 19.6% of students are overweight in this nurse's school district. That may not be the case. Maybe the percentage of overweight students in this nurse's school district really is higher, but the sample that she happened to collect didn't demonstrate that, right? Or maybe, you know, if this is the true population proportion of students who are overweight in her school district, then it is higher than 19.6%. So maybe if she got a larger sample size, maybe then we would be rejecting the null hypothesis. Okay, you see what I'm saying? So it's not that we're saying that the null hypothesis is true. We're not rejecting it, okay? But that doesn't mean it's true. That just means we don't have enough evidence to say that it isn't true. Okay, big difference there. And so you need to be careful with the way that you word your conclusion. You need to say this: there's not enough evidence to support the alternative. Okay. Typically, these problems will go a little quicker than this. If you're thinking, oh my goodness, these things are going to take me forever, they're really not. I'm kind of pausing and explaining things in a lot of detail to make sure that you understand all of everything that's going into this. But we're going to run through these problems a lot more quickly in the future. So let's look at another example, and we'll try to go through it a little more quickly. Okay. So this one says, in 1994, 52% of parents of children in high school felt it was a serious problem that high school students were not being taught enough math and science. A recent survey found that 356 of 800 parents of children in high school felt this way. Do parents feel differently today than they did in 1994? Use a 0.05 level of significance. Okay, let's do this. So first we need to state the null and alternative hypotheses. The null hypothesis is that no, parents still feel the same way that they did in 1994, right? 52% of them still feel this way, right? That their kids aren't being taught enough math and science. The alternative hypothesis is that parents feel differently. It doesn't say that the percentage is less or greater. It just says that it's different, right? So this is going to be a two-tailed test. Okay. Now, at this point, it's not totally necessary to compute the sample proportion, but I like to compute the sample proportion before we run the test in StatCrunch because it gives me some intuition in terms of whether or not I think we're going to be rejecting the null. So our sample proportion is going to be 356 out of 800, right? So let's see. How much is that? So that's 0.445. Okay, which is definitely smaller than 0.52. So it's different, but is it different enough? I don't know, to be honest with you. I think this might be kind of a close call. So let's run the test then. So steps 2 and 3, right? Test statistic and p-value. These are going to be done in StatCrunch. Go stat, proportion stats, one sample with summary. We're going to be prompted to enter the number of successes. That would be 356. And the number of trials, that would be 800. Let's see what we get. So stat, proportion stats, one sample with summary. So we have 356 out of 800. We want to test p equals 0.52 against p not equal to 0.52. So its default setting is to run a two-tailed test, which is what we want in this case. So we'll leave that as a not equals. Okay, so our test statistic is this number right here, negative 4.25-ish. Our p-value is tiny. Our p-value is so small, in fact, that StatCrunch doesn't have enough digits to store it. So it's just telling us it's really small. It's less than 0.0001. Okay, so let's write those things down, right? So our test statistic, Z naught, is about negative 4.25. And our p-value is less than 0.0001. We don't know exactly what it is, but it's really small. It's less than 0.0001. Okay. Now we can make a decision. So again, we're going to compare our p-value. We don't know exactly what it is, but it's less than 0.0001. So I'm just going to use 0.0001 in its place. And we want to compare that to alpha. In this problem, alpha, we were told to use a 0.05 level of significance. So we're comparing it to 0.05. We want the p-value to be less than alpha. Okay, if the p-value is less than alpha, then we reject the null hypothesis. And in this case, it is, right? It's much smaller. So, so since our p-value is less than alpha, right? So we reject. We reject the null. Okay. Again, your decision, the decision that you're trying to make is always whether or not to reject the null hypothesis. And the way that you make the decision is you compare your p-value to alpha. If the p-value is less than alpha, you reject the null hypothesis. Okay, so there's our decision. Now let's write a conclusion. So the conclusion, we need to state our level of significance. So at the alpha equals 0.05 level of significance, we're rejecting the null hypothesis, okay? So that means there is sufficient evidence to support the alternative, okay? Another way to say that is to say the evidence supports the claim that parents feel differently today than they did in 1994. So that's what I'm going to say. That's how I'm going to phrase it. So at the 0.05 level of significance, the evidence suggests that parents feel differently than they did in 1994. Feel differently about what? Well, they feel differently about the amount of math and science that their children were being taught. So you could write that. You could say parents feel differently than they did in 1994 about the amount of math and science their children were being taught. Or are being taught. Okay, so at the 0.05 level of significance, the evidence suggests that parents feel differently than they did in 1994 about the amount of math and science their children are taught. Okay, and that's our conclusion to that problem. Okay, I think I have one more example. Okay, so one more example, number 3. It says, according to the MAA, 1% of bachelor's degrees in the United States are awarded in the fields of math and statistics. A recent math graduate collects a simple random sample of 12,317 recent college grads and finds that 148 graduates majored in math or statistics. Does this evidence indicate that the percentage of bachelor's degrees awarded in the fields of math and statistics is actually greater than 1%? Okay, so that's our alternative hypothesis right there, right? Does the evidence indicate that the percentage is greater than 1%? Okay, so our null hypothesis, of course, is that it's not, right? Our null hypothesis is that P equals 1%, right? No change, no difference. The alternative is that P is greater than 1%. So that's step 1. What sample evidence does she have? Well, she went out and sampled over 12,000 people. And out of the people that she sampled, 148 of them, right? 148 of them had a math or science, or a math or statistics degree. So her p hat value was 148 out of 12,317. Let's see how much that is. That's about 0.012. So it is a little bit bigger than 0.01. It's not that much bigger than 0.01. However, she has such a huge sample size that I think she stands a good chance of being able to reject the null hypothesis here. But let's see. So steps 2 and 3, we're going to run in StatCrunch. We're going to go stat, proportion stats, one sample, with summary. We're going to enter the number of successes. That's right, having a math degree means that you're a success. And the number of observations, 12,317. Okay, let's see what we get. So proportion stats, one sample with summary. We have 148 successes out of 12,317 observations. We want to test P equals 0.01 against P greater than 0.01. Let's compute. Okay, so there's our P value. So our test statistic was about 2.25, and our P value was 0.0123. We can compare our P value to alpha now to make our decision. In this case, we were told to use a 0.10 level of significance. So alpha is 0.10. In order to reject the null hypothesis, we need the P value to be less than alpha. And in this case, it is, right? So we're definitely, so we reject the null. That means there's evidence to support the alternative. So at the alpha equals 0.10 level of significance. I'm just going to abbreviate level of significance. So at the alpha equals 0.10 level of significance, the evidence indicates that more than 1% of bachelor's degrees are awarded in the fields of math and stats. So more than 1%, yes, but probably not very much more, right? So like 1.2%. So more than 1%, but not that much more. This kind of raises a good question of like, sometimes you find that there is a statistically significant difference, but there's not a practically significant difference. It's like here, yeah, you know, 1.2% is statistically larger than 1%, but that's mainly because our sample size was so huge. In reality, there's really not that much difference, right? Nevertheless, this is what you would write for your conclusion in this problem. That concludes our discussion of 10.2. Looking at your homework real quick, it says don't use StatCrunch for 7, 9, and 11. You can ignore that. Use StatCrunch on all of them. Okay, so that's it.